All right, hi everybody. My name is Daniel, for those of you who don't know who I am, and today we're going to be going through a review of the entirety of Physics 158, which is a very big course. So we aren't going to be able to cover like every single thing, but we're going to try and like talk about enough of the topics and enough of detail that you can like do well in the course. Okay, so here's a little overview of how this is going to work. So the course is split into kind of 4 sections. So we have circuits, electricity, magnetism, and then we combine it all together at the end. So we're going to go through them and cover all these topics in as much detail as we can. Again, we won't be able to get through everything. And also, if I make any mistakes, feel free to like point me out because I'm also in this course, so I actually don't know everything. So please tell me if I'm wrong so that I don't tell you all the wrong things, just to be clear. Okay, we'll start off right from the beginning. So circuits. A circuit is a series of like circuit elements. So like anything which can bear a load is like a resistor. And there's like 2 basic types of circuits. So we have series circuits and parallel circuits. You can also combine them and you'll get stuff which is like not series or parallel. But for the most part, it can be broken down into series and parallel. So a series circuit is going to be when the elements in the circuit all have the same current. And then it's going to be parallel when they all have the same voltage. So though there's some different rules which come with series and parallel circuits. So first of all, when we're adding resistors in series and in parallel, the equivalent resistance in series is just the sum of all the resistors. And then in parallel, 1 over the equivalent resistance is the reciprocals of all the other resistances. And if you have just 2 resistors in parallel, you can also simplify it. So it's just like R1, R2 divided by R1 plus R2. And you can remember that if you want. It's a little shortcut, but it's not super necessary. Yeah. So then we'll move on to some of our, like one of the big things with doing circuit analysis is like the key principle is Kirchhoff's loop laws. So you got your current law and your voltage law. So your current law says that the sum of all the currents at a junction is 0. So what does that actually mean? So we can think about this as, because charges have to be conserved, all the charges which enter somewhere in the circuit all have to come out of the circuit again. So if you have like one wire going in and 2 wires out, the sum of the 2 wires coming out has to equal the current going in. And then we also have our voltage laws. So this says that as you go around any closed loop of the circuit, so in this we have an example here. For example, the top triangle, right? There isn't actually any battery or source of EMF in there, but if you go around in a loop, the sum of the voltage drops has to be 0, because you can't go around and still have potential at the end, right? Because that means that your electron, which is slowly going around your circuit, can still do more work, which would break some laws of conservation probably. So yeah, the trick with this is when you're creating your loop like equations, so like you can make a system of equations to solve for the currents, make sure you pick loops which are significantly different from each other. Otherwise, you could get like a linearly dependent system. So for example, this is an example here. If you make your one loop the outside of the diamond, your other loop the top triangle, and your other loop the bottom triangle, if you add those together, your top triangle plus your bottom triangle is actually equal to the outside diamond, because the current at the top, one of them is positive, one of them is negative because of how you've defined the direction. And when you do that, those parts of the equations will cancel and you'll just get the outside. So make sure you try and just pick current loops that are like really different and you'll avoid that problem. Yeah, that's the big thing there. Okay, now we'll jump straight into RC circuits. So an RC circuit is when you have resistors combined with capacitors. So capacitors store and discharge charges and electrical energy, and they do this exponentially. So when you're charging a capacitor, that's on the top there. So your current starts at a peak, which is when there's no charge on the capacitor, and it decays exponentially. And then the charge on the capacitor increases exponentially until the highest amount, which is when the voltage across the capacitor is equal to like, you can think of it like how hard the battery is like pushing. So it's like if you just have a capacitor and a battery, it'll have the same voltage as the battery. Because then when you go around the loop, none of your resistors in the loop will have a voltage drop, if that makes sense. Because all the voltage drop is coming from the capacitor, which means your current at your resistors will be 0, or it'll like approach 0. Yeah, and then the trick with like doing RC circuits is initially it acts like a wire, and after a long time it acts like an open switch. So next we have RL circuits. Similar idea to RC circuits, but now we're doing with inductors. So inductors resist changes in current. So it just like locks whatever is happening in the current in the circuit at that time. So if you turn on a switch and you had no current initially, you'll start with no current in the inductor, and it'll slowly come up to act like an ideal wire. And it's doing this through like magnetic induction, which we'll talk about later. And yeah, so initially an inductor acts like an open switch. So you can, when you're doing your circuit diagrams and you're like, oh, it like just like, the question will say like right after the switch is closed, you can just like pretend the part of the circuit with the inductor is not there, because no current will flow through that part of the circuit. And after a long time, it just acts like a wire. So same thing there. Okay, now we can combine our RL circuits with RC circuits, and we get RLC circuits. So these are circuits which have like an oscillatory behavior, because the energy in the circuit gets transferred between the capacitor and the inductor. So this behaves just like a spring. So like in physics 157, we had the oscillating springs. It's exactly the same idea, except all of our like numbers and constants are different. Also a note here, this is an RL circuit. It's just an RLC circuit without a resistor. So it'll oscillate like without decay. So as you can see in the top right corner there, you have a decaying oscillation, which decays exponentially. But without the resistor, it's like undamped. So it just like oscillates back and forth. Yeah, so then down there's your resonance frequency. So as you can see, when you don't have a resistor, that last term goes to 0, and it's just the square root of 1 over LC. Yeah, so this is just like a spring. You can think about it. It's just putting the energy from the inductor into the capacitor back into the inductor. Okay, next we talked about AC circuits. So AC circuits, as opposed to DC circuits, which we were kind of talking about earlier, they're circuits where the power source has an oscillating voltage, which means it's not constant, and there are times where it is 0. This presents some problems with doing math, because the time average of voltage or anything over time is 0 because it's oscillating. And so that's why we use RMS for voltage, which is the root mean square. Anyways, the VRMS, it's given by that formula there. It's just the peak voltage, which is like the amplitude of your voltage wave, divided by the square root of 2. And you can do all the math we do with circuits. If you use all RMS or all peak, it all works out nicely, because all you're doing is you're scaling it all by square root 2. Yeah. Okay, next we're going to talk about the voltage and current in different circuit elements in an RLC like AC circuit. So this is where we start talking about phasors, which are a little confusing. To be completely honest with you, they're like totally abstract, but they work really well to do the math with circuits, which is why we use them in this course. So the key thing is that the voltage in the resistor, so these graphs here are showing voltage versus time in the different circuit elements. I realize I didn't label them, but it's resistor, and then capacitor, and then inductor, like in that order. So a resistor, the voltage in the resistor is always the same as the voltage in like the power source, because the voltage drop in the resistor is related to the current, right? It's like V equals IR. So if there's no current, because the voltage source is not producing a voltage, there's no voltage drop in the resistor. Next, capacitors, we say they lag the current. Now this is really confusing, because in the graph, it looks like the voltage of the capacitor comes like first, if that or like it comes afterwards. No, it does come first, sorry. But the reason this makes sense is because in the graphs, you're not like reading it left to right, it's like through time. So you have to think about like what wave is hitting you first. So with a capacitor, the voltage from the battery will come first, the peak, and then it'll be the peak in the capacitor. And it's always off by a phase of like pi over 2. So we do our phasors, which is the next slide. But yeah, let me finish here. So inductors, they always lead the current. So the voltage through the inductor is always pi over 2 ahead of, or 90 degrees ahead of the voltage in the power source. So next we'll talk about a little bit about phasors. So you can see here the different phasors here. So we have the one for the inductor up there, and then the capacitor and the resistor. And you can see what I meant about it's rotating counterclockwise, right? So the voltage through the inductor will peak before the current peaks through the inductor. So yeah, we use phasors to solve different AC problems. And we do this geometrically because it's just like they're vectors. And they're rotating vectors in like, you can just think about them as vectors that are rotating. And the real part is the projection of the phasor onto the horizontal axis. And this, you can just like, you can do the math geometrically. So there's different rules. So there's like the impedance of our different, the different voltages. So the impedance is like the resistance equivalent of an, so you'll have your impedance of your inductor and the impedance of the capacitor, or the reactivity or something. I don't actually remember what it's called. Anyways, you can add those. Because they're all 90 degrees, you can do it like vectors. So the impedance of the capacitors and the inductors will add like this way, and then you have your resistor the other way. So you can first find the impedance in the like capacitor direction, if that makes sense. And then you can add that by like taking the square root to get the magnitude. And the angles are just, so you have your psi here. That angle is the phase angle, so it's the angle between the current and the source voltage. And that's just going to be tan of like the impedance of the inductor minus the impedance of the capacitor, which gives you the like this component of it. And then you have your resistor, like your resistance basically. Does that kind of make sense? That was not the most incredible explanation of phasors, but are there any? Okay. Next, when doing series or parallel circuits with AC, you have to, the same rules apply. So in series, the currents are all the same. So you line up all your current vectors. And in parallel, the voltage drops are all the same. So you like draw your phasors with the voltages in line. And so at this example circuit here, you have 2 elements in series and 1 element in parallel with the other 2. So you would first get, you'd first do it for the part of it that's in series, and then you'd get like a equivalent voltage drop across those elements, and then you'd align that phasor up with its voltage with the voltage across the capacitor. Yeah. It was a little confusing, not the best explanation. It's a little hard to explain because it's like totally abstract and not a real thing. It just models what happens really well. Yeah. Okay, are we good to move on from phasors? Okay. Next, we'll start talking about electrostatics and electricity, which is the next part of the course. So we started with Coulomb's law. So Coulomb's law relates the force between 2 charged particles to the magnitude of their charges divided by the distance between them squared times some constant k, which is 8.99 times 10 to the 9 units. I don't remember what the units are. They're probably important, but yeah, anyways. So force is a vector, like every other force. It's no different for electric charges. And you add them just like vectors. So you take their components, and you can get the angles between them. This stuff is relatively straightforward, but there are some tricks to the question. So you can have like dipoles where you have 1 positive charge and 1 negative charge. And then the y component would cancel because you have your forces going 90 degrees to each other. And then you're only left with an x component. Yeah, and it's just vector addition with our charges. And then don't forget the sign on the charges matters. So positives, like charges repel and opposite charges will attract. And you kind of have to just look at where the charges are to decide which way the forces will go. Also, don't forget that the force is applied to both charges. So it's not just one charge applying a force to the other charge, because we have Newton's second law. Is it the second law? third law? Is it third law? Okay, every force has to have a reaction, right? So the charges both apply forces on each other. Awesome. Now we move on to electric fields. So an electric field is something which you can think of as it's what you would multiply. If you put a charge in the electric field, it's the direction is like the force it would experience or the direction it would go. So our field is defined, it's just the Coulomb's law, but you take one of the charges out. So it's just kq over r squared. And the field is also a vector, and so you add fields like vectors by taking their components and adding them likewise. So field lines are a way of modeling electric fields. The direction of the lines are always the direction a positive charge would go if you put it there. And the density of the field lines is related to the intensity of the electric field. Yeah. Okay, now we'll talk a little bit about how we can calculate electric fields in like continuous distributions. So this would be like a uniformly charged rod or a uniformly charged sheet. And the way you do this is you split up your rod into all like the little pieces, like small, infinitesimally small pieces, and treat them all like individual charges, applying one force or one field at like point B, for example, and you integrate over the length of the rod. And one key thing to realize here is because the field is a vector, you have to do the integration in vectors. So you have to first find the x component and the y component, or the y component and the x component. But you can use symmetry to simplify a lot of problems here. So in this case, because one rod is positive and the other one is negative, your fields are going to go 90 degrees to each other, and so you're actually not going to get a y component. It's just going to be 0. So you can look at it right away and not do any integration for this because it'll save you time. It'll just be 0. And then we don't really have time to go into the math too much. It's just, yeah, you would split it up into like the individual charges, and then you would find the individual fields, so like all the DEs, and then you just integrate that, and it works out to be this integral, and this would give you the x component of the field at B. Yeah. Okay. Next, we're going to talk about conductors and electric shielding and what conductors do when you put them into an electric field. So because in a conductor, the electrons are free to move, when they experience an external field, they will move, right? Because if you place a charge in an electric field, it moves. So if you put a conductor into an electric field, all the free electrons start to move. But because the electrons move, you'll get accumulation of negative charges on one side, and you'll get like accumulation of positive charges, which are like holes of electrons on the other sides. And because you have a difference in charges, you get an induced electric field in the opposite direction of the external field. Because you have an external field this way, so your positive charges go this way, and your negative charges go this way. So then you get an induced field this way. And these charges go in these directions until the induced field is the same magnitude as the external field. And then they stop. And at this point, there's no net field inside of the conductor, which is why conductors always have a field of 0 inside of them, and all of the charges are always distributed on the outside. Yeah, the key with doing these types of problems is make sure that the charges are conserved. So if it tells you that there is a charge of Q on this thing, once you've distributed your charges such that the fields cancel, there should still be a net charge of Q on the object. Does that make sense? Okay. Next, we'll do a quick overview of Gauss's law. So Gauss's law is super useful in solving electrostatic problems and with electric fields and stuff. And the formula is true always, but finding the surface integral of like really hard shapes is totally beyond the scope of this class. And so you'll only ever look at like 3 shapes. You'll have a rectangular prism, a sphere, or a cylinder. And in the case of the rectangular prism and the cylinder, you're generally only looking at it for like one side of it. So you'll use the prism for a flat sheet because the flux is only through like the top of it because the sides are parallel. And then you would use a cylinder for like a rod or something, like a really long rod. And when you're doing Gauss's law with long cylinders and long rods, we ignore the ends of the cylinder because we say that it's negligible compared to the field through the tube part of the cylinder. Yeah. Okay. Next, we'll talk a little bit about electric potential. So electric potential is like energy per unit charge. Or sorry, it's like field. No, it is energy per unit charge. And potential is really helpful for solving electric field problems because it's directly related to the electric field. Because the electric field is the gradient, the negative gradient of the potential. The gradient's like the 3D slope, basically. And because potential is a scalar, doing math with potentials is way easier than doing math with fields. So you can find the potential at a point, take its position, like the derivative of its position, and you get the electric field, which makes solving problems really a lot easier than integrating for the electric field, because you have to do that in components. So yeah, there's this fancy math symbol. It's like nabla or something, but it's literally just the partial derivative with respect to position in the 3 dimensions. So if it's only changing in the x direction, it's just the derivative of the potential with respect to x. Yeah. Okay, now we'll look really quickly at calculating potential of like a charged sphere. So we know that the potential is just the final. So we say the one trick with doing these is we always integrate outwards. Which means we want our final position to be further away from the center than our initial position, because that gets rid of any chances of negative sign errors. So we say that the final potential minus the initial potential is equal to the negative integral from like our initial position to our final position of the electric field in this area. So in this situation, we're going to have we'll have 4 distinct areas of field. So there is like outside of the entire sphere, just out to free space. And then, actually, sorry, 3, because we assume that the outer disk has like negligible thickness. Then we look at the field inside the shell, outside of the inner sphere. And then there's also a different field inside the inner sphere. So first, you say your final potential at like an infinite distance is 0. So we set that to be 0. We find for our initial voltage, which is like the voltage on potential on the outside of the sphere, and we do that by just integrating from the field outside of the sphere. Then we do that again, this time setting our final voltage to be that initial voltage we had just found at the outside of the sphere, and then we start at the outside of that little sphere and integrate across the field in between the shells. Then we do that again, taking the voltage, the potential we found at the surface of the shell, and we take that as our new final voltage and setting our initial voltage or potential as the potential at the center of the sphere, using the field inside of the sphere. Does that make sense? So like it'll look, this is a graph. It's showing how the potential changes at different points as you change your distance. And one key takeaway is that the potential across a conductor doesn't change, because it's like an ideal wire in a circuit, right? We say that there's no potential drop in an ideal wire. It's the exact same thing with conductors because there's no field. So you're integrating 0, basically. Yeah. Okay. Next, we'll talk a little bit about energy and work in electric fields. So electric potential energy is just something's charge times the potential, electric potential at that point. And so we can find the potential energy of a system of particles. We just consider all the potentials between all the particles, if that makes sense. So you'd have, say you have 3 particles, 1, 2, and 3. You'd first find the potential between the first 2, then you'd find the potential between the other 2, and then you'd find the potential energy between the last 2. And you just add up all their potential energy, because energy is a scalar, and that gives you the potential energy of the entire system. And then work done by like us to the system is just the charge that we're moving times the change in potential from initial to final. Yeah, because work is just the change in internal energy internal energy is QV, so work is Q delta V. Does that make sense? Key thing to remember with work is that it's only because electric fields, the forces always go like in the direction of the field. If you have a particle moving like diagonally across a capacitor, for example, because the fields are always going horizontally, it's the same work as if you moved it straight across the capacitor, because the change in potential is the same in both situations. Does that make sense? Obviously, you still have to do some other work. You're doing work to something because you're moving it, but the work for the electric potential energy is only the horizontal part. Okay, now I'll talk specifically about, there's one example they really like is capacitors and dielectrics and like pushing a dielectric into a capacitor. So the internal energy of a capacitor is given by 1/2 CV squared. And when you put a dielectric into a capacitor, what you're doing is you're changing the electric permittivity of the space in between the capacitors. So E0 is a constant which represents like how hard it is to make an electric field in that like medium. And when you put something in there, you change how hard it is. So you change E, or epsilon, by a factor of K. And K is like some empirical constant they'll always give you. So this applies for any problem involving capacitors, is whatever you do to E0 by multiplying it by K, it'll somehow factor in to how it'll change like your capacitance or the energy stored in the capacitor. It's all just scaled by K, if that makes sense. Or like, you have to follow through the math, but it's always just the E which is scaled by K. So wherever you have an E, it's times K. And that'll always work with capacitors and dielectrics. Also, if you're putting a dielectric into a capacitor, it gets like sucked in because of how the forces work out. But finding that force is really, really hard. But it turns out really nicely that the force is just the negative derivative of the potential energy of the capacitor. And the way you do this is you split the capacitor into two pieces. So you treat it as two capacitors that are in parallel. So you have one capacitor which has air in it, and another capacitor which is completely a dielectric. And you find the energy stored in both of those capacitors together as a function of x, like how deep the dielectric is into the capacitor. And then that gives you a function of u in terms of x. If you differentiate that with respect to x, you'll get the force in the x direction. And it'll always be inwards. So if you ever have your force going outwards, it's probably the wrong way. Okay, now we'll start talking about magnetism. So just like electric fields, we have magnetic fields, which is denoted by B. And when you move charges through magnetic fields, they experience a force. And the direction of the force is the cross product of its velocity with the magnetic field times its charge. So there's lots of different ways of doing the right-hand rule. My personal favorite way of doing it is you take the first thing you're crossing with your index finger, and then you do the second thing with your middle finger, and then your thumb is the product. So you have V, B, and then the force goes up. You can also do it with the thumb, but I find that confusing. But you do whatever works best for you. It all is equivalent. So yeah. One key thing with forces and magnetic fields is because it's the cross product, the direction of the force is always perpendicular to the direction the thing is traveling, which means that a magnetic field can do no work to anything ever, because the force is always perpendicular to the distance it travels, and the work is given by the force dotted into the distance. So it'll always be 0, which means particles always travel at constant speed in magnetic fields, which is why you can get circular motion with magnetic fields. Okay, now we'll talk about forces and torques on current-carrying wires. So a wire is just a collection of charged particles moving. So you can get Q and V because current is like charges per second. So if you multiply the charges per second by the length of the thing, you get the number of total charge, which is the Q in QV cross into B, and then V is related to how fast they're moving, which comes from the current. So that's where that formula comes from. It's just IL crossed into B, and it's not I crossed into B, it's actually the vector L crossed into B, which is, well, it's actually, yeah, it's always going to be, actually it is I actually don't know why it's L crossed into B, but it's just the direction of the current, the magnetic field, and then the force. Same thing with charges moving. Next, if you have a loop of wire, it has a magnetic moment, which is not actually a real thing. It's just something that comes out of the math. But it works nicely because the magnetic moment of a loop, it doesn't have to be a circle. It could be like some weird rectangle shape. Its magnetic moment always wants to align with the external magnetic field. So the way you find the direction of the magnetic moment is you have a loop of current. You take your right hand and you curl it in the direction of the current, and the direction your thumb goes, which will be perpendicular to the plane of the loop, is its magnetic moment. So there's two states of equilibrium here. It can be fully aligned, or it can be completely inverted to the magnetic field, which is like an unstable equilibrium, because if it's like angled at all, it'll just flip round all the way, if that makes sense. Yeah, the magnetic moment is just the current times the area of the thing, and the torque is the magnetic moment times the field. Yeah, you can also find the torques by looking at the forces on the individual parts of the loop, but that can get a little confusing with like weird shaped things. So you can just look at the magnetic moment, and it's much easier, I think. Okay, next we'll look at the magnetic field, which is generated by a wire. So charges moving generate magnetic fields, and a wire is a collection of charges. So you can, all the little like magnetic fields generated are all components of all the charges moving along the wire. So you can get all the little bits of, you can get the magnetic field from all the little bits of wire, which is where Biot-Savart's law come from, which is just like, and you can integrate that over some length because it's a differential with respect to the length. So you take Biot-Savart's law, say you have like a meter long wire, you just integrate it from 0 to 1, and that gives you the magnetic field at some, in terms of R, basically. And then if you have a really long wire, infinitely long wire, you end up with mu naught I over 2 pi R, which is an important one to remember. It's not actually on the formula sheet, so it's useful to know this one. You can also derive it using Ampere's law, which we'll talk about in a second. But yeah, that's for a really long wire. Next, we'll talk about magnetic flux. So magnetic flux can be thought about like it's the dot product of the magnetic field dotted into the area of some surface, which is kind of telling you how well aligned the surface is with the field. So if it's at 90 degrees to the field, you'll have no flux because the dot product will be 0, because the area vector, like with Gauss's law, the area vector is perpendicular to the surface, and we say it's going away from the object. So yeah, so this works out to generally work out to just be b times a cosine theta, where cosine theta is the angle between the a vector and the field. So if they're perfectly aligned, it's just the field times a. Also, the magnetic flux through a closed surface is always 0 because you can't have magnetic monopoles, because magnetic field lines are always connected end to end. Okay, next we'll talk about Ampere's law. So Ampere's law is like the magnetic equivalent of Gauss's law for magnetism. And it has very similar form to Gauss's law. And it's just the surface integral of the field and, or sorry, not the surface integral. It's like a loop. So you have a loop around a current carrying wire, and the field at every point along that loop is the same if it's like very symmetrical. So same with Gauss's law, you can't use this at all times, but if you have a straight wire, if you draw a circular loop around the wire, you know the field everywhere at that wire is the same, and it'll be in a circle, because just like you can use our right hand rule again, so we point our thumb in the direction of the current, and the direction our thumb curls will be the direction of all the magnetic fields around the wire. So this is very useful when we have symmetry. So like I said earlier, we can find the magnetic field at around a long straight wire using Ampere's law as well, because it's just a closed loop around a long wire, which we know it's current. So it'll work out to be the circumference, which is 2 pi r, and then mu naught I. So then the field is just mu naught I over 2 pi r, which is exactly what we got using Biot-Savar's law. Next, we'll talk quickly about solenoids, which can be, we use Ampere's law when looking at solenoids. Solenoids are cool because if the solenoid is long enough, the field inside of the solenoid is really strong, and the field outside of the solenoid is like basically zero. So if you ever have a question when you have a really long solenoid and like a charge moving outside the solenoid and asks you like what happens, remember that the field is zero outside of the solenoid if it's really long. And then the field inside of a solenoid is just related to the current going around the solenoid and the number of loops of current you have. Also, the direction of the field everywhere inside the solenoid is all the same. So it's not just that the center at the solenoid, it goes straight. It's actually, if it's long enough, everywhere inside the circle of the solenoid, it all points straight. So yeah. Okay, now we'll start combining topics from electricity and magnetism together and see how they influence each other. So there's Faraday's and Lenz's laws, which are kind of the same. One of them gives you the magnitude of an induced EMF. So if you change the magnetic flux, which is the dot product of the field and the area through a surface, if you change the flux, you're going to induce an EMF, which is like a voltage, basically, in that surface, or like a loop. And you'll induce it in the loop. And the direction of this is always going to be such that, and we know current also induces a magnetic field, right? So when we induce a current, the current starts flowing, that current induces its own magnetic field, which can impact the net magnetic field. And Lenz's law, or Faraday's law, I actually don't remember which one, says that it'll do so to resist any changes. So this is how an inductor works. So if we try and change something, the inductor will work against that. It's exactly the same here. So if I have a bunch of magnetic field going through a loop, and I turn the magnetic field off somehow, the loop wants to have the same amount of flux going through the loop, and so it's going to generate a current in the direction such that the induced magnetic field from the current is the same direction that the external field was going. So in this situation, it's this way. So we want our field to go this way, which means we want our current to go that way. So you'll have an induced current, like, I guess, what is this, clockwise. Now, say we take our same loop with no field, and we start sticking a field through it. The loop wants to have no flux going through it, and so it induces a current in the direction which cancels, to its best of its ability, the external field. So in this case, now we have a field going this way, so the loop wants to generate a field this way, and so it'll generate a current that way, or an EMF this way, which then generates a current. And you can get EMF in not a conductor, it just won't cause current, which is, yeah. Make sure when you're differentiating the flux, because the flux is like a function of B and A and theta, all of which can change with respect to time, make sure you do the chain rule when you take the derivative, otherwise you'll lose some factor in your derivative. Yeah. Okay. Next, we'll quickly talk about moving conductors in magnetic fields. So just like before, a conductor is a bunch of electrons. So if you move it, it's the same as moving a charge through a field, and it'll experience a force, which is given by the field times the length times the speed which it's moving, if it's like perpendicular to the field. That comes from the Lorentz force. There's a bunch of situations where this comes up. Most of it is with rails, like you'll have a rail sliding in a magnetic field. And so when you move the rail, it changes the flux through that loop, which induces an EMF. But then because you have the rail moving, it experiences its own force separate from that, if that makes sense. So in this example here, the rod is moving that way. So the area of that loop is increasing. So the flux through the loop is increasing. So it wants to decrease the flux again. So it'll generate a current this way, such that the magnetic field comes out of the page, because there's an external one into the page, which is increasing. So you'll have a current going this way, which means there's an induced EMF like down through that wire or that rod. But then you also have a conductor moving through a magnetic field. So you do your cross product, so you have this guy, and so you have a force, yes. It'll experience a force, which way does the force go? Up? Oh yeah, it'll go up. So you'll have an induced current up, or an EMF up, because all the charges in the rod want to go up. Because it's going this way, the field is into the page, so the force it experiences up, or is an EMF which goes up. So now you have two competing things. You have the induced EMF from the area changing, generating a current down, and you also have an EMF going up because of the thing moving. And it'll reach like a terminal velocity when those two EMFs are equal. If that makes sense? Okay. Yeah, induced electric fields. This kind of came up earlier, but changing magnetic fields generates circular electric fields, just like an electric field generates circular magnetic fields. So if you have a bunch of magnetic fields and you like increase their strength, you'll generate like fields going in circles around the magnetic fields. Yeah. And this goes in a loop. So you change your electric fields, induces magnetic fields. The magnetic fields that you've induced are changing, and changing magnetic fields induce electric fields. So now you have more changing electric fields, and this goes on. It doesn't really stop. It'll stop happening eventually, but in theory, you just have one field induce the other field, and they keep like going 90 degrees to each other, and you'll have a bunch of fields inducing each other, which indicates they're probably related somehow. So our main relation between them, so this guy Maxwell came along, and he looked at all our formulas and was like, they're all really similar. And one thing he did, which is why he gets credit for the equations, is he realized that when you're charging a capacitor, there's like current missing from, like it doesn't add up. There's not enough current. So he introduced displacement current, which is like totally weird because it's not a current and nothing is moving. And all it is it's just the electric field changing, which is the same as a current. Like mathematically, a current and changing electric field are the same. So he called it a current. And then when you add that into the equation, then you get the Ampere Maxwell law. I have a feeling that probably won't come up very often in like actual math. But you never know. Sorry, that was kind of, but yeah. So here are Maxwell's equations. They relate the magnetic fields with so you have Gauss's law and Ampere's law are related. They look really similar. And then Faraday's law and the Ampere-Maxwell law relate changing magnetic fields to the changing like electric fields, basically. So yeah, so we can come along and we can solve Maxwell's equations, and then we get two wave equations, which again, I don't think you're going to have to do any math with the wave equations. But they are wave equations, so if you combine the waves, you get electromagnetic waves, which are light. So these come out of a result of solving those equations, because in all the equations, if we go back, you can see that all of them have electric fields and magnetic fields in the same equations, and you have 4 equations, so you can solve them and have it such that you have one equation that is only magnetic stuff in it, and one equation with only electric stuff in it. And those give you electromagnetic waves. And there's also the speed of the wave, which is the displacement factor in front of the wave. It works out to be the square root of 1 over mu naught E naught, which is the speed of light, which is cool, which means electromagnetic waves are light. So there's lots of questions they can ask you about like different types of light. So you have like your radio waves, microwaves. These are probably all like multiple choice questions. Yeah, the direction of the waves is also important. So it's always like propagating perpendicular to the electric and magnetic fields. So it's the cross product of the electric field into the magnetic field. So just like before, we take their electric field and our magnetic field. The direction of propagation is forwards. And this works even when they're oscillating because it's like these parts decrease and then they go that way. And they keep doing that. And the direction doesn't change. So it's always going this way, if that makes sense. It's like, yeah. So yeah, that's light. Again, I think the light stuff will be very light on the math part. There's not a pun. Because it's kind of out of the scope of our course. But you do have to kind of have a conceptual understanding of what light is and how it's related to electric and magnetic waves. Oh, sorry. Okay, that's most of the course. There's a lot of stuff we didn't talk about because it's such a giant course, but I hope we went over most of the big stuff. So yeah, if you would like to, we'd really appreciate if you gave us some feedback on how this went, so you can fill out this QR code. We'd really love if you fill out some feedback. Thank you all for coming. I hope you learned something or remembered something from earlier in the course. Good luck studying, and yeah, hopefully we all do very well. So yeah.